Well, hello guys, Mr. G here, and today we're going to be doing a video for the work, energy and power test. This is the first part, so will be questions 1 and 2. And the first one is a multiple choice as usual. Here is the examiner was Professor Rodriguez, and then we're going to start. But before starting, please remember to subscribe for the channel so you can get the notification, the worksheets, and all the information I post on a daily basis. So we're going to start with the question 1. Question 1, as usual, multiple choice, and the question said a block moved from rest in a straight line under the influence of a constant net force. This is an important detail in this specific question. The force is going to keep constant. It's a net force. Which one of the following graphs best represent the net work on the block in relation to its displacement? You have to remember that net work is going to be equal to net force multiplied by the displacement multiplied by the cosine of theta. Okay, now we are going to keep the net force constant. It's said in the question it is constant. So what is the relation between a net work and displacement? And also the angle must stay constant. So if the angle stays constant, the net force, the net work, depend on the displacement in a directly proportional relationship, as you can see there. So which one would be the correct answer? If you increase the displacement, then net work will also increase in a direct proportional relationship, and the correct answer will be B for question 1.1. I hope you did get that one when you answered the worksheet. Question 1.2. The sketch below show a block that moves to the right in a positive x direction through the displacement delta x. Note that the displacement in each case was to the right. This is going to be the displacement to the right in all the cases. And the question said, while under the influence of a force with the same magnitude F, and the magnitude of the force in all the cases is going to be the same. In which one of the cases will the amount of work done by the force F will be the greater? Okay, if we go to the first one, you can see that the angle between the force and the displacement is 90 degrees, and therefore the work done by this force is equal to 0. You can see that one. This one here is the same. If you use the formula, work done by this force, let's write the formula perhaps a little bit more here. Work done by the force, by the applied force, is equal to the force multiplied by the displacement multiplied by the cosine of the angle. This angle here is different to 0. Okay, so it will be different than 0. If we go to D, for instance, there you will see that it's in the opposite direction. So therefore, this work done by the force is going to be a negative work done. It's going to be negative. And this one here, the angle is equal to theta. You know that cos 0 degree is equal to 1. So this C will give you the greatest work done by that force. That will be the correct answer, because cos of any angle that is different than 0 will be smaller than the cos of 0, which is 1. So I hope that one is clear. It's not that bad. Let's go to the next one. A boy of mass M jumped from a tree branch at the same time that a girl, also of mass M, begin her descent down a frictionless slide. So the girl moved through a slide and the boy jumped from a tree. That is important to know. Begins her descent from a frictionless slide. The friction, there is no friction in the slide. If the boys start at the same height above the ground, which one of the following is true about the kinetic energies as they reach the ground? And then I want you to note what is going on here. The boy is jumping from certain height straight down, but the girl slides from the same height, but the girl is going to go through the slide. So what happened here is that the girl is going to move through here. They leave this point at the same time, and the boy, this is the girl, this is the boy. Boy move down straight, as you can see there, but the girl uses the slide. And the question said which one of the following is true about the kinetic energy as they reach the ground. And something important, that the mass of the boy is equal to the mass of the girl. That is an important detail here. Well, guys, kinetic energy, if you remember, kinetic energy is equal to half the mass speed square. That is an important detail here. Second, both places are frictionless. There is not friction for either of them, and therefore the mechanical energy is going to be conserved. So for each case, it is starting from rest, and therefore you can say that the mechanical energy initial must be equal to the mechanical energy final. All right, I'm talking about either of them individual, but it will be the same for both of them independent of the path taken. Initial is only potential energy, and final is only kinetic energy, guys. That is important. So the kinetic energy at the end is going to be equal to the potential energy at the beginning, which is mass, acceleration due to gravity, multiplied by height. Now here is the thing. Mass is the same. G is constant, and height is also the same. That was what we started here. Therefore, the kinetic energy is the same for both of them. So the correct answer would be C. They have the same kinetic energy. It's a good question, this one. Question 1.4. An applied force F accelerates an object of mass m on a horizontal frictionless surface from a velocity v to a velocity of 2v over a distance delta x. The net work done on the object is equal to, and they give you 4 different options there. And for this question, we are going to apply the work energy theorem. Net work is equal to the change in kinetic energy. Net work, which is what we're actually looking for, is equal to half mass final speed square minus half mass initial speed square. And we are going to substitute the values here. The mass, remember, is a common factor, so we can actually say that the net work is equal to half mass bracket. Now final velocity is 2v, 2v square everything, minus initial speed is going to be just v, so is v squared. And we solve this one here. When we solve this one, we have that is half mass here bracket, there is 4v squared. Be careful with this one, it can give you or get you confused. A minus v squared, and that is what we have for now. So net work is going to be equal to half mass, and now this one here is equal to 3v squared. You can see you can solve that part, there can be solved, and then it's 3v squared. And if you rearrange this one, you have that is equal to 3 divided by 2 mass v squared. It's a very good question. That is what we have at the end, and therefore the correct answer is B. I hope you got that one previously when you answered the worksheet. Question 5 and the last one of the multiple choice. Question 1.5 said to lift a car with a hydraulic lift at the service station at constant speed require work to be done. Lifting the car twice as high requires, and they give you different options there. And obviously, if you increase the distance twice the height, therefore the work done by that force must be also twice. So we have 2 options here, A and B, that said twice the work done. But the first one say twice the work done by the same power, and the other one said twice the work done and half the power, which is not correct. You need the same power, and therefore the answer for 1.5 is A. And guys, we are done with question 1. Let's go to question 2. I hope question 1 was clear. You can always go back, watch the video, and ask question if those any of those was not Correct. Now question 2, and the final one for this video. A skier with a mass of 80 kilograms start from rest at A. So at A, the speed is equal to 0. And the mass is 80 kilograms. The mass of the man, I'm going to write it here, mass is equal to 80 kilograms. Start from rest. The ski slope downward is rounded while a point C. The ski slope downward is rounded while at point C the slope is upward inclined. So you can see that it's gone down all the way to C and then it's going again up. The grounded downward loop is frictionless. So this loop, this side here does not have friction. Friction there is 0. There is not friction. While the upward incline is a rough plane. So here, friction on this side here is not going to be 0. Friction there is present. Now state the law of conservation of mechanical energy in words. And this one was a grade 10 topic. It is a very simple, so we're going to quickly answer that question 2.1 real fast here. And this law states that the total mechanical energy, total is important, in an isolated system remains constant. So total mechanical energy in an isolated system remains constant. Remember, mechanical energy is equal to the addition of kinetic plus potential. That is important also to remember, but you don't have to say it right now. And this is the first question here. 2.1, state the law of conservation of mechanical energy in words. Second question, name a conservative force acting on the ski while he moved down. Now, conservative force, there is a video I done a little bit long time ago. You can watch that video. I'm going to leave the link for this conservative force. You can see the link up here. Now, important here, the only conservative force you are doing in South Africa is going to be the gravitational force. There are more conservative forces, but the only one done in South Africa is the gravitational force, and therefore I am going to write here gravitational force. That is the only conservative force you do in South Africa. There are more, guys. If anybody is watching from overseas, then it's more. There is electrostatic, elastic, and so on. But we are going to be talking about gravitational force. It's the only conservative force in this question here. Question 2.3, use the law of conservation of mechanical energy to calculate the speed of the ski at point C. Now, from point B to C, it can be calculated, or from point A, doesn't really matter, because there is not friction, the system is isolated. So at that point, you can calculate the law of conservation of mechanical energy. And for this question, I'm going to take points A and point C. Okay, so those are the 2 points I'm going to take to answer that question real fast. So we're going to go to a new page. And here we are. We're going to start by saying that the mechanical energy, the total mechanical energy initial is equal to the total mechanical energy final. And remember, I said we're going to work with points A and C. So we are actually talking about the mechanical energy total at A, and is going to be equal to the mechanical energy total at C. Remember, we said that mechanical energy is potential plus kinetic, or kinetic plus potential. So mechanical energy at A is going to be equal to kinetic energy, I'm going to write at A, plus potential energy at A. That must be equal to kinetic energy at C plus potential energy at C. And if you go to the formulas, which they are just here, guys, is the formula for a potential energy. Here you can see the formula here for potential energy. There we go. And then the formula for kinetic energy is on the other side here. The symbol K is the same use as well as U for potential energy. So those are the formula. Go to the formulas there so you can get the formula. So if we substitute here, we have half the mass multiplied by the speed at A square plus mass multiplied by g multiplied by the height at a. Here on the other side you have half mass, the speed of the object at c, which is what we in actual fact looking for, plus mass, acceleration due to gravity, height at c. And then all we have to do is to substitute what we have, which we have in actual fact everything. And this, guys, is what you have. You can see that it started from rest, so this is 0, and at the end, right at c, there is not height, therefore this one is also 0. So here you will have that this product there will be 39,200, and this is equal to 40 v square. Guys, this is simple math. V must be equal to the square root of 39,200 divided by 40, and that will give you the final speed, or the speed at c, which is the question. This is speed at c. Let's keep that c there. Then the answer will be 31,30 meters per second. That is the speed at point C, guys, and that is the answer for this specific question. So we continue with question 2.4. The skier experienced a kinetic frictional force of 160 Newton while he moved up the slope. So the frictional force is different than 0 and is going to be equal to, I'm going to write it here, the frictional force is going to be equal to 160 in Newton. It's given to you, guys, so you need it. Now then they said, while he moved up the slope, draw a level free body diagram to show all the forces acting on the skis when he moved up the slope. So what forces are acting on the ski? We're going to do that question here on the right. So what forces are acting on that ski there? First, we're going to draw one roughly here, right here. The is going to be the x-axis. In this case, we're going to write displacement for this topic. This one is the y-axis, and now what forces are acting there? Remember, these axes are going to be perpendicular there. So what forces are acting on the ski? The frictional force backward all the way straight down the slope. This is the frictional force. There is a normal force perpendicular to the surface. Be careful with that one. And then is also weight straight down here. This one is weight. So those are the three forces acting on the object, and therefore the free body diagram that they want must be exactly like that one, which means frictional force in this direction. This one is weight straight down, and then make sure the frictional force is perpendicular to the normal. This is a way to make sure it is corrected drawn. And guys, this one is the symbol notation is not necessarily here, but it should be done there. And this one here, guys, is question 2.4.1. This is the free body diagram they want you to draw. This one I have on the little bit to the left towards the center of the page is the one we need for the solution, but this one is the one for marks. And just for control, if you do it like this, you'll get 1 mark per force, okay? But it's not the important right now. Use the energy principles to calculate the greatest height reached by the skiers from C. Now, the greatest height means that is the height when the skiers is going to stop. Now, something important, energy principles that can be used here, guys. There are 2 energy principles that can in actual fact be used here. And those 2 energy principles are either work energy theorem, which you know, net work equal to change in kinetic energy. That is one option that can be used here. Or you can also use the law of conservation of energy. And this one is the one that says that the work done by the non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. So these are the 2 options that you can actually use here. Those 2. either work energy theorem or the law of conservation of energy. And now I wanted to go to the formulas again real fast. I'm sure you're working with formulas with you. I'm sure you have it right now. Here on top, this side here, is the work energy theorem. You can see it there. Just you have two, because it's two different symbols, nothing else. It's the same thing, so it's different symbol. And this one here on this side down towards the left is the law of conservation of energy. Both of them are given to you in the exam. So why will you struggle to learn something you don't have to? All you need to remember is that the blue one here is the work energy theorem, and the purple one here down left is the law of conservation of energy. And whenever they said use energy principle, you can use either of them. So let's go back to the question and select which one we are going to use. Well, we can use either one. Let's use the work energy theorem in this case, guys, but I recommend you to then try to use the other method and compare the answers and see if you are able to do it. You can contact me. It's not a problem. You can send me a message if you are not sure about the law of conservation of energy. Let's use the work energy theorem, but you can use both of them. Now, this one here is not the same. This one is something also important. This one is not the same. This one is the law of conservation of mechanical energy. This one here, the law of conservation of energy, is the one that actually states energy cannot be created nor destroyed, only change from one type to another. That one is this one. This one is always going to be conserved, but the one top 2.1 is only conserved if the system is isolated. So for this one, we're going to use the work energy theorem, but you can use any of them. If I'm going to use the work energy theorem, I would like for you to do the law of conservation of energy, because it's a practice. Sometimes they leave it open like this one, but sometimes they ask you to do to use the law of conservation of energy, for example. Then you cannot use the work energy theorem. So we're going without talking. I've been talking too much. The network, we're going to use the work energy theorem. So network is equal to the change in kinetic energy. And using our free body diagram, which I'm going to bring here because it's really important, which ones are, or what is the network? Well, network here would be the addition of the work done by normal, which by now you know in this case is also 0, plus the work done by frictional force, plus the work done by weight, and that is equal to the change in kinetic energy, which we can actually write everything there. Let's just try to fix this one. This one is half mass final speed square minus half mass initial speed square, and this is what we're going to do as usual. Remember, if you've been following me, remember I like to work separated. Now, by now, we're going to calculate the work done by friction first of all, real fast. So the work done by friction is equal to the frictional force multiplied by the displacement multiplied by the cosine of, and by now you also should know that this one is 180 degrees here. You go to the free body diagram, displacement is in that direction pointing up there, so the angle here is, as you can see there, 180 degree. Okay, so when you substitute, you have all the values here which we are going to substitute. But we have a tiny issue here, guys. Tiny problem. We have a very tiny problem there. We unfortunately don't have the displacement, and let's quickly go back to the question. We don't have the displacement, but nothing to worry about, because we have here this maximum height, and you can see that I'm forming here a triangle right angle. H, I also don't have it, but I am looking for it. And if you use this one is 90 degree here. As you can see, there is 90 degree, and therefore I have that the hypotenuse will be the displacement. Okay, if you use maths here, you can see that sin theta, which is 30, I'm going to write the 30 there, sin theta is equal to opposite side, which is h, divided by the hypotenuse, which is delta x. And guys, here is what we are going to use instead of the displacement. So that one, we are going to substitute it there. So here we have to know that this one, that tan theta or 30 degrees equal to h divided by the displacement. And if you rearrange this one for displacement, you can see that the displacement is going to be equal to the h divided by tan 30 degree. Now all this one can be substituted in there. So let's do that one real fast. So we have now that the work done by friction is equal to friction, which is 160 multiplied by the displacement, but the displacement is h divided by tan 30 degree multiplied by the cosine of 180 degree. When you solve this one, you have that the work done by frictional force is equal to minus 160h divided by tan 30. We have two unknowns, so we have to stop there, guys. So this is what we have for the work done by friction. And therefore, we're going to stop right here. Now, let's go to the work done by weight. Work done by weight. But here, before we go to weight, let's get rid of the work done by normal. You know it's 0 because the angle is 0. So we're going back to the work done by weight. Now here, what is the angle between displacement and weight? The angle will be this one here. If you watch my videos, remember I explained how it is solved. So this one here will be 90 plus the angle of the slope, which is 30 degrees. So this will be the angle between the displacement and the weight. Remember, this one here corresponds to 30 degrees, which is the angle of inclination there. So saying that, we can now attempt to calculate the work done by weight. And I said attempt because we will have to and no as well. But work done by weight will be equal to weight, but weight is equal to mass multiplied by acceleration due to gravity, multiplied by displacement, which remember we have it there. So displacement multiplied by the cosine of 90 plus 30 is equal to 120 degrees here. And now if we substitute what we have, which is what we are going to do real fast here, we get that this one is minus 392 h divided by tan 30. But we can also solve this one, and the answer would be 700 minus 784 h. This is what we have now for the work done by weight. If you go back here, you can actually divide by tan 30 if you want. It's not a big issue. The answer here, if you do that, will be then 320 minus 320 h, and that may be easier to substitute then. So now we're taking this one here and we're taking this one here and we substitute in the formula of work, which is here on this side there. We can actually now substitute everything we have, guys. So we're going to do it real fast here. So we are here, then we can substitute everything. I am not going to write the 0 there. For friction, we have negative 320 h, plus for weight we have minus 784 h, and that is equal to half. The mass is 80. The final speed is 0 because we say how high can it go up until stop. Actual fact, as for the greatest height, so the greatest height is when the object on the main, in this case, stop. I'm not going to write this. Let's write the square. Half the mass is 80, and the initial speed here is the one we calculated at point C, which it was 31,3 30 meters per second, and this is going to be square. And guys, the rest here is the calculation there. So let's do the calculation real fast. And the answer is going to be 35,469 meters, guys. This is the answer for this question. As you can see, it's a little bit tricky. It's a very good question, if I may, and this is the answer for that specific question. You go back, remember to try to do, you don't have to do it exactly the same way as I did. Some people like to substitute all the formulas here and then substitute there, but it will come very long and you may forget certain things. That is why I like to do it step by step and separated, calculating each the work done by each force separated. But let's go to the last question of this activity, or question 2. And the question said, the angle between the inclined plane and the horizontal is increased from 30 to 50. So the inclination now here is not 30 anymore, it's going to be 50. So it's bigger inclination. What effect will the enlarged angle have on kinetic frictional force working on the skis? And for this one, let's have a look down to another page. Guys, for this question, all we have to check is how to calculate the frictional force. Now, the frictional force, remember, the kinetic frictional force in this case is equal to the kinetic coefficient of friction multiplied by the normal. Now, what is the issue? The kinetic coefficient of friction is going to be the same. The kinetic coefficient of friction is the same because the surface didn't change. What changes was the angle. So this angle here is not 30 anymore, it's going to be 50. So 30 is for the first scenario, and for the second scenario is going to be 50 degrees. That is for the second scenario. I hope you understand what I'm saying. Note that in this free body diagram you must add the components of the weight, which in this case is here you will have, in this case, weight in the y-axis, which if you remember is equal to weight multiplied by the cosine of theta, which in this case you have two thetas, 30 for the first scenario and you have 50 for the second scenario. And you also project to the x, is not part of this problem right now, but you will also project to the x having the weight in the x axis. Now, if you see here, the normal will be equal to the weight in the y-axis. This is in actual fact applying Newton's first law, with many examples like this one. And then when you substitute, you have that is mg cos of theta. Now, if theta was 30 degrees, then cos 30 will get one number. If theta was 50 degrees, then cos 50 will give you a different number. And let's do this one quickly. Cos 30 degrees is equal to 0.87. 0.87. Note the following: I am not calculating normal, I just calculating the cos, because normal will then, as you can hear, the normal will definitely depend on the angle. That is why I'm calculating the cos for each of them to see what happened. And here with the new scenario will be cos of 50 degrees, which is 0.64, and as you can see, the cos of 50 is smaller than the cos of 30, and therefore the normal now with the new scenario is going to be smaller, and therefore the frictional force is also going to be smaller. And then we can answer the equation here. The question said, choose from increase, decrease, or remain the same. The correct answer is decrease. They don't say you must justify, but if that is the case, guys, you can go back and see what happened in this example. Thank you for watching. This is the end of the video. And saying that, subscribe for the channel. Don't forget to subscribe. You can ask questions, suggest. I'll see you next time with the second part of this test, which are questions 3 as you can see here, and question 4 as you can see there. Thank you. I'll see you next time. Mr. G here.